All right, I want to take a look at our next problem, problem 8 here on our review of functions. As we're looking at this next problem, it talks about the cost C and profit P functions in dollars for producing and selling X radios are represented by the following graph. Now in this graph, you'll see two functions, two linear functions graphed in here, and they represent the revenue and cost functions for this company that we're looking at that produces radios. And so the x-axis represents, you see here, the radio. And let me highlight this. Right, it represents the radios being produced and sold, the number. All right, so we've got, for example, here at 100 on the x-axis, that's 100 radios that were produced and sold by this company. Now on the y-axis, you see these different dollar amounts. So we got $5,000, right? $10,000, and so forth. And you see graphed over here to the side are your revenue and cost functions, which are needed to calculate profit. So if you remember, profit is revenue minus cost. Right? So again, I want to make note of that. Put a little note over here to the side. Profit is revenue minus cost. So with that said, let's look at some of the problems that come from the graphs of these revenue and cost functions. In part A, it says evaluate and interpret C of 0. So we're talking about the cost function. Now C of 0, remember we're looking at 0 here as the input. So we're going to be looking at this value of X, right? So that means what happens when we produce no radios? What's the cost going to be for this company? So we don't sell or produce any radios. What will we have for a cost? So let's go ahead and calculate that. So we know our cost function, right, is represented by 10,000 plus 100 X. So we got 100 over 3 times 0, right? So we plug that in. Now as we simplify, it simplifies easily to 10,000 plus 0, right? So we've come up with 10,000. Remember, this is a dollar amount, the output. So remember, Y represents dollars, X represents number of radios being produced and sold. So there's our answer here to part A. Now $10,000, all right, is the cost. Cost for the company, all right, if they produce and sell 0 radios. All right. Now, as we look at our next example, example B. So example A, review and evaluation of functions. And example 2 reviews solving a function. So now it wants to know when will cost be $20,000, right? C of X equal 20,000. So let's go ahead and write that down. So our cost function, so we got 10,000 plus 100 X equal to 20,000. Now as we solve this, we're solving what? A linear equation. So let's go ahead and solve that together. And we'll go ahead and move the constant term over. We're going to isolate the X term. So we'll go ahead and subtract 10,000 on both sides. All right, and as we do that, as we reduce, our equation now reads 100 X equal to 10,000. And now we got to get rid of coefficient. So we got a coefficient out here in front, right? 100. Now I'm going to go ahead and multiply by the reciprocal, right? So we can clear that out. Right, so the hundreds divide out 3, multiply by the reciprocal, we get a product of 1. And over here, let's go ahead and reduce. Right, we got 100 into 10,000. So we know 100 into 10,000, that goes in there, what, 100 times? So we can reduce that. Right, 100 times 100 would give us 10,000. And then 100 times 3 is 300. Right, so X we've solved it. So that implies X is equal to 300. And remember, that represents radios. 300 radios produced and sold with a cost of $20,000. Right? So again, interpreting that, it will cost $20,000, right, to produce 300 radios. All right. Let's go to part C. Part C says evaluate and interpret R of 500. All right. Well, now we're looking at the revenue function. So we're going to take a look at R of X, right? So now we've got an input. So there's my input, right? X and equals 500. So out goes X in our revenue function. And in comes 500. And remember, now this is representing the number of radios being produced and sold. So R of 500 would equal 50 times 500. And as we simplify that, 50 times 500 is 25,000. All right. And again, this represents revenues. This is a dollar amount, right? The output. So the company's revenue, so let's go ahead and write down what we found here. Let's interpret it. The company's revenue will be $25,000. All right, if they produce and sell 500 radios. All right. And let's go to part D. Part D says solve and interpret R of X equal 35,000. So now I want to find out what X is. We want to know how many radios we need to produce and sell to make a revenue of $35,000 for this company. So let's go ahead and set that up. So our revenue function, which is 50X equal to 35,000. So we're solving a basic, right, linear equation. Go ahead and isolate the X term. We can go ahead and divide out on both sides 50. And as we simplify down, right, we have X, which is what we were looking for, right? X, which is the number of radios that needs to be produced and sold to get this $35,000 revenue. Well, 35,000 divided by 50 is 700. 50 times 700, right, gives us 35,000. And again, this represents radios, right, produced and sold. So interpreting, 700 radios produced and sold, revenue, right, is $35,000. All right, let's look at the last one. So part E says, when does revenue equal cost? So let's find out when revenue equal cost, which revenue equal cost is when our profit is zero, or what we call our break-even point. I like to make note of that here beside it. When does the company break even? So let's find out. So as we take our revenue function, so R of X, which is 50X, we will know an equal cost, and cost is what? 10,000 plus 100/3 X. So again, we got a linear equation to go solve. All right, now it might be, to make this problem a little easier, let's go ahead and clear out the fractions. All right, so that's going to be my first step. So I'll make that note. Clear the fractions. All right, so to do that, we need our LCD, our least common denominator, right, which is 3. So I'm going to go ahead and multiply, right, both sides of this equation. I'm going to use a multiplication property equality just to simplify things nicely. Multiply everything by 3 so I can divide out this denominator, right? Get rid of that fraction, clear it. Now 50 times 3 we know is 150. So 150x. 10,000 times 3 is 30,000. plus 100 thirds times 3 is 100. So to me, it looks a lot better now. I like to clear out fractions when I'm solving an equation like this one for x, which had a fraction in it. And now I'm going to go ahead and get the x terms together. So we're going to move that over. Let's go ahead and apply our addition property of equality and add a negative 100x, or subtract 100x on both sides, right, to group the x terms. We're solving x. We want to get x by itself. As we do that, 150x minus 100x, we have 50x equal to 30,000. And then we're ready to divide out 50 on both sides, and we'll have what we're looking for. Right? So as we do that, what's 30,000 divided by 50? Well, that gives me what, 600? So x is 600. So here it is. So 600 radios, right, produced and sold, right, will allow our company to break even. That's when revenue will equal the cost, which is at $30,000, which will result in a profit of 0. So again, there's the value of x as we solve that. So this is the break-even point, 600 radios, right? Revenue will equal cost at $30,000. Revenue will equal cost at 30K. Or profit is 0. All right, so that's, again, break-even point. All right. So that summarizes Module 3, or I should say Module 2, when we're defining functions. So we're looking at evaluation of functions, solving functions, observing graphs, reading graphs. All right, now let's move on to our next examples, which come out of our next module, Module 3. And in Module 3, we're looking at transformations. So we start to look at how to easily translate a graph of a parent function to get to the function we're looking for, so we could get a quick sketch. We want to be able to quickly sketch a function graph knowing our transformation properties. And we talked about in Module 3 our transformation properties, which include stretching, right, and compressing your graph horizontally or vertically. Also talked about reflecting your graph about the x or y axis. And then we talked about how a graph shifts horizontally and vertically. So we're going to review those characteristics, how to recognize these properties, and so we can apply them to our graphs, the functions we're looking for. Now in our first problem, let's read through this first example. It says, write the equation of the function f of x equal x squared, translated 6 units to the left and down 7 units, then graph it, get a quick sketch. Well, with that said, all right, we're talking about our squaring function, a quadratic function y equal x squared, our parabola. And I will show you the y equal x squared graph over here on the side. All right, we'll go ahead and graph in y equal x squared. And y equal x squared, just to show a couple of points, it's your U-shaped graph, right, through the origin. So we'll go ahead and graph that. A quick sketch here of that. So it's got a U shape to it, and just to show a quick sketch. Here's my parent function, y equal x squared, right? Just to label a couple points. We know it passes through 1, 1, negative 1, 1. And we could make as many points as we wanted with that said. But I want to translate this graph by shifting it left 6 units. So I'm going to go ahead and show that. So if we were to shift left 6 units, right, what that causes with our transformation, I'm going to write that down here. Shift y equal x squared graph, our parent function. All right. Left 6 units. All right. A horizontal shift comes into play when we add or subtract a constant to our domain variable x. So what that would do to our equation, y equals x squared, our parent model, right, we got to go inside here with x, and to go left, we would have to add a 6 or subtract. I like to show it as this. Subtract a -6 from your x term. Right? We're going left 6 units. So again, we're going to subtract a negative number. Now as we do that, right, let's simplify that down. Right? What does that equal? That implies y equal x plus 6 squared. So when you're looking at a horizontal shift, it's opposite of what you might think. When somebody says x plus 6, wouldn't you go right 6? Wouldn't you add 6 to every x coordinate? We're actually subtracting a -6. So every x coordinate, we would subtract 6 from it. So if you want to show that graphically, over here, for example, let's take our points that we've plotted here on this parent function. If we were to go left 6 units, right, our graph, right, we would subtract 6 in the y coordinates, so now we'd be at -6, 0. For example, -1, 1. If we went left 6 units, right, we would be at -7, 1. And we take 1, 1, and we go left 6 units. What's 1 minus 6? 1 minus 6 is -5. So that will put us over here at -5, 1. So just to show that, I'm going to dash in my new graph, this function. So there it is, shifted left, and just to plot those points. All right, there's our graph now. So left 6. All right. Make a note here. And now we're going to our final translation. It says down 7 units. So now we want to shift. So this is what we call a vertical shift. Shift graph down 7 units. Now as our equation goes, all right, we've got our equation of y equal to x plus 6 squared. Right now we've shifted left 6 units. Well, to go down, right, 7 units. And let me write this. I'm going to go ahead and put this in a different color. Let's keep that in black, right, just to clearly see the translation that took place into your equation. Anytime we go vertical with our shifts, we're adding or subtracting a constant to the function, not to x. When you add or subtract a constant to your x term, your domain variable, you affect an x coordinates, which moves it left and right. If you add or subtract a constant to your function, like y equals x squared, or if you had y equal absolute value, or square root function, whatever the parent function is, adding a constant moves it up that many units. Subtracting a constant moves it down that many units. So going down 7 units, we would need to subtract a 7 from that function. That would cause it to go down 7 units. Right? So there's our final piece. Now you wanted to show that graphically, we could easily do that. So what's down 7 from -6, 0? We would subtract 7 from the y coordinate. That'd put us down here at the point -6, -7. And like -5, 1, what's down 7 units? Well, 1 minus 7 is -6. So we would go down here and plot this point of -5, -6. And for example, -7, 1, right? If we go down 6 units, we would be at -7, -6. So I'll go ahead and plot that point just to show the translation. And again, your graph, which I'll put it in blue now, here's a quick sketch of this function graph. So there's the graph of f of x. So here's f of x equal to x plus 6 squared minus 7. There's this graph there in blue. So yeah, you've got your function now. So f of x equals x plus 6 squared minus 7. So again, let's apply our transformation properties. A little review on that problem of horizontal and vertical shifts. All right, but there's the equation, right? We added a 6 to the x term to move it left 6, right? And we're looking at x in the squared function. And then we subtracted the 7 to move it down 7 units. So again, that's an example of a couple of our transformation properties. All right, well, let's move on. Let's do another example. Let's do a square root function. Let's look at problem 2 and see what we have in this one. In problem 2, we're looking at a parent function. All right, so I'm going to go ahead and talk about our parent model. So we'll put that here beside it. When I see problem 2, the first thing I'm thinking is y equals x squared x. Right? All square root functions, right, come from the graph of y equals the square root of x. So if you want, let's build a quick sketch of the square root of x function. So just to show you square root of x, well, you could build a table of points, right, if you wanted to apply the translations. But I know that, for example, square root of 0 is 0. I know the square root function. It begins here at 0, 0. I know domain of all even roots, like square root of x, 4th root of x, 6th root of x. We've got to have x being greater than or equal to 0 because you can't take the even root of a negative. So you'll notice the domain, all these x values, all these points take place at 0 or any positive number. So take place on the positive side of the right axis, including 0. Now, for example, we could let x be 1. We all know the square root of 1 is 1. 1 1's on that graph. We could let x be 4. What's the square root of 4? Square root of 4 is 2. Right? So right now, if you're looking at the graph of our square root function, here's y equals square root of x. That's the parent function. Now, what I want to do is graph f of x. So we're going to talk about the changes that take place. And I'll circle them. There's 3 transformations in this problem. I've highlighted them right here. So the first thing I'm going to do, all right, is I'm going to talk about this negative inside here. What does this do? Let's list the transformations. So the negative, right, inside here, that causes my graph to reflect. So we're going to reflect the graph, right, of y equals square root of x, which we already have graphed over here to the side. We're going to reflect it about the y-axis. Anytime you multiply your domain variable x by a negative, it's going to flip your graph across the y-axis. It's going to take every ordered pair, and I'll write that down. All right, let's put it up here. Every ordered pair, every point x, y, you will find the ordered pair negative x, y on your graph. So for example, 1, 1, if we reflect across the y-axis, we would be at negative 1, 1. 4, 2, we reflect across the y-axis, we would be at negative 4, 2. So right now, this would be our graph. I'll dash it in just to show you again a sketch. There's y equal to square root of negative x. That takes care of the negative. It flips it across the y-axis. It multiplies every x coordinate by a negative. So you can see that translation. All right, now that takes care of that negative. Now I want to look at this 2. What does that do to my graph? Well, when you multiply your function by a constant, you're going to be stretching or shrinking, or sometimes referred to as compressing, your graph vertically by the y-axis. So a stretch or a compression comes into play vertically. Now, with this number being greater than 1, right, we have a coefficient of 2 here. This implies we're going to have a vertical stretch. So let's write it down, our transformation. Vertical stretch by a factor of 2. All right? Well, let's go ahead and take that. So if we stretch this graph vertically by a factor of 2, all right, I'm going to go ahead and show that. So as we're looking at our points right now, negative 1, 1, right? Negative 1, 1. We would multiply each y coordinate by 2. 1 times 1 is 2. So it would move to negative 1, 2, right? Negative 4, 2. We multiply the y coordinate by 2. We would move up here to negative 4, 4. Right? So I'm going to plot a couple of these points. negative 4, 4, right? Negative 1, 2. Right? 0, 0, of course, multiplying the y coordinate by 2 wouldn't change anything. But just showing you here in red. Right, here's our graph. This would be the graph of y equal to 2, right? Square roots of negative x. So there's the stretch vertically. And now we have one last change to take place. And let's look at it. So let's go ahead and talk about this minus 3 on the outside. All right, and we'll go down here and write down the effect of it. Now, subtracting a 3 from the function, mentioned this in our last example, causes a vertical shift down 3. So plus we go up, minus we go down. We're adding or subtracting a constant outside the function. Shift down 3 units. So as we were to finish off our graph, this point 0, 0, if we go down 3 units, let's shift all these points down. We're going to subtract 3 from every y coordinate. So we're going to be beginning now here at the point 0, negative 3. All right, where's that point negative 1, 2 move? Well, take the y coordinate, subtract 3 from it. What's 2 minus 3? Negative 1. So that negative 1, 2 point is going to move down here to negative 1, negative 1. Right? So we could plot that point, negative 1, negative 1. Where's negative 4, 4 move to? Well, so we subtract 4, or we subtract 3 from 4, we get 1. So move down here to negative 4, 1. So we'll go ahead and plot that point right here at negative 4, 1. All right. Now our graph, I'm going to go ahead and put it here again in this green color. All right. You can see our graph shifted down. Again, I'm going to plot that point here, negative 4, 1. But there's my graph of my function. So there's f of x. So you can see I stepped it off step by step. F of x. So there's our function. F of x equal to 2 square roots of negative x minus 3. All right, just walking off the transformation. So that one had the vertical stretch and reflection property introduced into that one. All right. So again, that's reviewing transformations. A couple examples. We'll take a break and we'll continue on and look at some more. All right. But this is getting into transformation properties.